Okay, hello Analysis 1A. This is an old homework. So either you did it and you're ready to hand it in on a moment's notice, or you didn't. But it's from about a week ago. We are in week 8 now, but this is the week 7 homework, so we're going to hand this in ASAP. And what's up with that week 7 homework? Well, we were just learning the chain rule at the beginning of week 7, and the homework that was due, I want to say it was due midweek of last week, was some homework on the chain rule and also some homework on the product rule and quotient rule. So this page 148 over here, this was section 3.3 on the product rule and quotient rule, and this was section 3.4 on the chain rule. And I believe these problems are actually a bit harder, these early ones, and we didn't go over these in any class. So let's do it right now. Here we go. Number 84 is a kind of a strange problem, actually very much like a problem we did in class just yesterday. It gives you two functions and then it says, verify that their derivatives are the same and explain the relationship between f and g. So I think what they were expecting you to do is to just blindly jump in and use the quotient rule. But, you know, I'm sorry, but I'm just too experienced to just blindly use the quotient rule, because I see that I can split this fraction up into two pieces, and that's just going to make it a lot easier. So what do I get here? I get sine x over x minus 3, and here I get sine x over x plus 2. And already the mystery is solved. What are these two functions, f and g? They're basically just the same function. This sine x over x function, which is a function that we graphed a million times, here in f it's being moved down 3, and in g it's being moved up 2. So what are these two functions, f and g? They are just vertical translations of each other. They are right on top of each other. One is just 5 more than the other. And so, of course, they're going to have the same derivative, because they really are just the exact same function, but just translated vertically. All their tangent lines are, of course, going to have the same slope at every single moment, because these two functions are doing the exact same thing at every single moment. They're increasing at the same rate. If you want to think of it from a position and velocity perspective, then these are two functions whose positions are different. In fact, they begin 5 apart from each other. But at every single moment, these two functions stay 5 apart from each other, because f is, or g is always just going to be 5 more than f. I don't know where to write that exactly, so maybe I'll just put it here, right? In fact, the relationship between g and f is that g is just f plus 5. So once you determine that, then it's sort of obvious that these two functions are going to have the same derivative, and this sort of explains everything. Okay, let's do it really quick. How do I take the derivative of this function? Well, for the derivative of sine x over x, now I really do want to use the quotient rule, so let's do it. Derivative of the top, so the derivative of sine is cosine, so derivative of the top times the bottom minus the top times the derivative of the bottom, so minus sine x all over the bottom squared. So that is my formula for the derivative. Of course, the derivative of negative 3 is just 0. And, okay, I mean, it's just completely ridiculous for me to do the quotient rule again, because it's just the exact same thing. So I'll just say, you know, this equals f prime, and we're really just kind of done. So what do these two functions look like? Well, we know what sine x over x looks like, because we've graphed this a million times. It has this kind of you know, this 1 over x envelope, and okay, I mean, I really almost like don't want to do this, so maybe I should just stop since I'm in charge. But the function is going to be 0 near the origin. That was the one that was kind of like a mystery, but by the time I get to pi over 2, I guess, which is like 1.5, I'm going to be up here at this point. So, and then, you know, later on at pi, which is actually going to be off my board, I'll sort of be back again. So it's going to have this kind of shape in which that's negative pi, in which it's even and it kind of goes up and down. I sort of picked a bad scale here, I realize now. this function. Maybe just erase this and just do a much worse job that only takes like 1 second. This function, I just know from previous experience, has this shape that kind of looks like, and this one, so that's sine x over x. And what's my f function? It's just that moved down 3. And what's my g function? It's just that moved up 2. So of course they have the same derivative. Okay, going a little faster here, what do we find? This very interesting and sort of strange and maybe kind of difficult problem number 85, which I never go over because it's too time consuming to kind of draw this on the board. But in your textbook, you were given, in this number 85, a graph. In fact, 2 graphs. And they were given to you graphically. So they want to make sure that your understanding of the derivative is so flexible and expansive that you can be presented with a function by formula, but that you can also be presented with the function graphically. So this is kind of problem is testing your geometric reasoning. And so we're given 2 functions, f and g. We're not giving the formulas for those functions, we're just given graphs of those functions. And okay, what is the function f? It's maybe it's a bit hard to read in your book, but I've redrawn it here, hopefully pretty clearly. It's a piecewise, so-called piecewise linear function. It's a function which is linear in pieces. Okay, so okay, I think everyone knows what that means. And then what is g? G is also piecewise linear. So I've labeled all the kind of relevant points, and now we are given 2 new functions, p and q. What's p? P is the product of f and g, and q is the quotient of f and g. And we're being asked to find p prime of 1 and q prime of 4. Okay, so we really just get to it. There's nothing much to do here. If p is the product of f and g, then what is p prime? Well, here we're just kind of regurgitating now the product rule. What is the product rule? It says that the derivative of the product of 2 functions is the product of the first times the second plus the first times the derivative of the second. So there is the product rule in general. Okay, so what's p prime of 1? Well, p prime of 1 is just going to be f prime of 1, g of 1, plus f of 1 times g prime of 1. And so, okay, I guess they are sort of testing whether you sort of get it all. Well, okay, how do I find all of these numbers so that I may complete the problem? Well, you just look at the graph, right? What is f prime of 1? Well, now we see that x equals 1 is falling on this first line. And you are supposed to just look at this line and kind of squint and realize, okay, look, here I am at this point, which I promise you in the book it's very clear that it is 0, 5, and this point is 3, 8. So what have I done? From 0 to 3, I've gone over 3, and from 5 to 8, I've gone up 3. Therefore, the slope of this line is just 1. And if the slope of this line is 1, then the derivative of this function is just 1. In fact, the derivative of this function is 1 for the entire interval from 0 to 3. And that includes x equals 1. So f prime of 1 is just 1. Good. What is g of 1? Well, what is g of 1? This is actually a little bit annoying, maybe. G, I promise it's completely clear from the book, has a point at negative 1, 5. So this is negative 1, 5. And so now I kind of just need to plug 1 into this g function. Man, that's actually pretty annoying. Well, let's do it. Where am I? I am here at 5. And yeah, let's see. If my y-coordinate's 5, then I'm going to go down to 3. So my change in y was negative 2. And my change in x from negative 1 to 3 is 4. So I've gone sort of over 4, but down 2. Therefore, the slope of this line is negative 1/2. If the slope of this line is negative 1/2, then by the time I get to x equals 1, g is going to have gone down just by 1, right? So yeah. So there is so I guess the point is that there is a point here on the graph of g that you have to see, which is going to be 1, 4. because it takes me 2 to go down 1 and another 2 over to go down 1. I guess you could just, I guess in the book maybe it's even more obvious that when you plug 1 in, that the answer is 4, because it does go right through that point. Okay, point is, what is g of 1? It's 4. It's taking too long. And what is f of 1? Well, once again, there I'm being forced to do some like math or whatever, but if the slope of this line is 1, then by the time I get to x equals 1, f is going to be 6. So, because I started at 5. In other words, there's a point 1 comma 6 on the graph of f. And so f of 1 is 6. And what is g prime of 1? That is negative a half. And so the answer to this problem is 4 minus 3, which is 1. Okay, let's now do q prime of x. Well, q is the quotient of two functions, so in general, the derivative of q is going to be, well, I just used the quotient rule. It's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And that is the quotient rule in general, but I don't want the derivative in general, I want the derivative at 4. So the answer to this is going to be f prime of 4, g of 4, minus f of 4, g prime of 4. And I guess the point of this problem is to sort of make you put all of this together. That the quotient rule enables you to find a formula for the derivative of a quotient in general. If I want the derivative of a quotient at a particular point, then I need to find, basically, these are the 4 things that I need to know in order to be able to evaluate q prime of 4. So let's just go find them all right now. Well, let's see. First of all, this is a flat line here from 3, 3 to 6, 3 on the graph of g. So when I get to 4, it's still going to be 4, 3. And of course, it's also true that the slope of this line is 0 because it's a horizontal line. Okay, that's good to know. What's going on at 4 in the graph of f? Well, I'm here at 3, 8, and a little bit later I'm at 7, 4. So I've gone over 4, but I've also gone down 4. Therefore, the slope of this line is negative 1. So actually, this is kind of nice and easy. I'm at 3, 8. If the slope is negative 1, then by the time I get to 4, the slope will be, the y value will be 7. So what's relevant is that there is a point 4, 7 here on the graph of f. And in the book, it might even be easier to see that the line just really does go right through 4, 7, because in the book there's like a grid. But okay, great. So now we just do it, right? What is f prime of 4? We just said it's negative 1. What is g of 4? It's 3. G is the red function, minus f of 4, which is 7, times g prime of 4, which is 0, all over g of 4, which we said was 3, squared. So actually, what do we end up with? We end up with negative 3 in the numerator and 9 in the denominator, so the answer to this problem is negative 1/3. Okay, so that was maybe, a lot of effort or something, but there it is. Okay, be back in a second with some more. Okay, a couple more problems from this same section. Our book chooses to teach the concept of second derivative, third derivative, etc. within this section 3.3 on the product and quotient rule. So here are 2 little problems. This one says, hey, here's a function 4x to the 3/2. What is the second derivative of that function? Okay, so let's go. What is the first derivative of that function? Well, it's just a power rule situation. So 4 times 3/2 is just 6x to the 1/2, and then you just take the derivative again. That's what the second derivative is. It's just the derivative of the derivative. So what's the derivative of 6x to the 1/2? It's 6 times 1/2 x to the negative 1/2, and therefore I would report my final answer here as just 3 over root x. Okay, so that wasn't supposed to be hard or anything. This one, 103, someone said that they had some trouble with. Again, the directions are the same, so just find the second derivative. So, well, you just got to do it. There's no shortcut really. I will use the quotient rule. The derivative of e to the x over x. Okay, so it's the quotient rule. So derivative of the first, that's e to the x times the second minus the first times the derivative of the second, which is 1 all over bottom squared. So what does that get me? Just x e to the x minus e to the x over x squared. Let's see, does it make sense to simplify that? Hard to say. Alright, I wish the problem ended there, but it doesn't. It continues. Hold on, I was going to say something, but I forgot. Well, whatever. Okay, so let's now just take the second derivative. That's what the second derivative is. It's just the derivative of the derivative, so let me just differentiate this. Again, I'll just use the quotient rule. There might be a kind of a slightly faster way, but it's not going to be that much faster. Alright, let's go. How do I differentiate this quotient? Well, it's the derivative of the top times the bottom. So, okay, let's begin. How do I take the derivative of the top? Well, that's going to require the product rule, first of all. So, what is the derivative of x e to the x? Well, it's the derivative of the first, which is 1, times the second, plus the first, x times the derivative of the second. So that's just the derivative of x e to the x. Notice I had to do a product rule just kind of on the spot. Minus the derivative of e to the x is e to the x. So that whole thing I just computed was the derivative of the top. Yeah. Alright. Derivative of the top times the bottom minus the top. So that's x e to the x minus e to the x times the derivative of the bottom, which is 2x. All over the bottom squared. So there's just some sort of algebra going on here. Let's see, I mean, I guess you're free at any moment to just decide to stop. Should I double check my work or should I just trust myself? Derivative of the first times the second plus the first times the derivative of the second. Yeah, great. Well, these cancel, so that's something. So what do I end up with? I'll just kind of squeeze it in right here. It's going to be in the numerator x e to the x times x squared, so really that becomes x cubed. And now, let's see, that 2 to the x gets multiplied by x e to the x and subtracted, so it's going to be minus 2x squared e to the x, minus 2x squared e to the x. And then there's also going to be a plus 2x e to the x, plus 2x e to the x, all over x to the fourth. And now finally, I can factor an x out of, I can cancel an x out of every term and I can factor an e to the x out of every term. So I guess what I end up with is e to the x squared minus 2x plus 2 all over x cubed. And I bet that's how it's given in the back of the book. Something like that. Give me 1 second, because there were some opportunities there for mistakes. So I would hate to have that wrong. E to the x over x cubed. Yeah, that's right. E to the x over x cubed times x squared minus 2x plus 2. Okay, so, alright. I guess we've proven our point that, you know, the quotient rule is messy or something. Okay, let's do this last problem. It's really just 4 problems in one, and it's kind of a callback to what we did 5 minutes ago. Now you are once again computing the derivatives of sort of abstract theoretical functions defined in terms of other functions, but now instead of being given the graph by formula, instead of being given the function explicitly via formula, the previous problem you were given the functions by being shown a picture of the graph of the function. Now we're going to do something even more abstract, and we're just going to give you individual little tiny facts which are themselves sufficient to sort of do the problem. So let's go. What are we going to do? Oh, and the directions for every single problem are find f prime of 2. and we're given the value of g and h at 2 and the derivative of g and h at 2, which is kind of all we need. Okay, no more commentary, let's just do it. What's the derivative here? Well, it's going to be 2 times whatever the derivative of g is plus the derivative of h. So here I'm just using derivative of a sum as the sum of the derivatives and the constant rule. Okay, therefore f prime of 2 is going to be 2 times g prime, I guess I can write this, g prime of 2 plus h prime of 2. And that is going to be, well, what is g prime of 2? It's negative 2. So this is 2 times negative 2 plus, and h prime of 2 is 4. So I guess the answer I get here is just 0. Okay, moving on to 112. This is, f is just 4 minus h of x. So what's the derivative of f? Derivative of 4 is 0, so this is going to be negative the derivative of h. And therefore, what's the derivative of f at 2? It's going to be negative h prime of 2. And h prime of 2 is 4. So this is going to be just negative 4 is my answer here. Okay, how about 113? Well, now we just use the quotient rule, right? So what do we get? We get that the derivative of g over h is derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So, specifically f prime of 2 is g prime 2 h of 2 minus g of 2 h prime of 2 all over h of 2 quantity squared. The AP exam is a big fan of these kinds of problems because you can't sort of like cheat on them or like use a calculator or whatever. They really are like pure thinking problems that force you to demonstrate that you understand the quotient rule. So, okay. Anyway, let's just do it. What is g prime of 2? It's negative 2 times h of 2 is negative 1 minus g of 2 is 3 and h prime of 2 is 4 all over h of 2, which is negative 1, squared. So what do we end up with? I guess we end up with 2 minus 12. So that hopefully that's negative 10. I guess I could have kept myself on the same page there with checking this, but I guess that's probably right. Yep. And finally, 114, this should be a little bit easier because the product rule is easier. So what is the derivative of f now? It's the derivative of g, derivative of the first times the second plus the first times the derivative of the second. And therefore, what's f prime of 2? It's g prime of 2, h of 2 plus g of 2 times h prime of 2. And alright, therefore we just stick them all in, right? G prime of 2 is negative 2, h of 2 is negative 1, g of 2 is 3, and h prime of 2 is 4. So now that's 2 plus 12, so that's 14 is my answer for that last one. Okay, that finishes the first half of this homework. Let's go back and do all these chain rule problems now. Goodbye. Okay, we're back to do the rest of this homework. This was the first homework on the chain rule. Therefore, all these problems were pretty easy. I don't really have much to say, and we did some of them in class already. So let's go. Number 9 gives you this function, 2x minus 7 cubed. And asks you for the derivative of this function. Okay, this is just straightforward chain rule. The derivative of something cubed is 3 something squared back inside for the derivative of the something, which is the derivative of 2x minus 7 is just 2. So answer here is 6 times 2x minus 7 squared. Boom! 13 is the function 9 minus x squared to the 2/3. So what's the derivative? Answer, the derivative of something to the 2/3 is 2/3 something to the negative 1/3 back inside for the derivative of the something, and the derivative of 9 minus x squared is negative 2x. Therefore, the answer to this problem written out in a coherent way would be negative 4x over 3 times the cube root of 9 minus x squared. It's good to get in the habit, I think, of rewriting something to the negative 1/3 as 1 over that thing, 1 over the cube root of that thing. So that's what I did. Alright, 17 gives you a function now, also a cube root, but here they want to make sure that you understand that this is a power rule situation, so we're going to rewrite this in a derivative-friendly form as 9x squared plus 4 to the 1/3. And therefore, what's the derivative? Chain rule says the derivative of something to the 1/3 is 1/3 something to the negative 2/3 back inside for the derivative of the something, and the derivative of 9x squared plus 4 is 18x. So let's see, the 18 cancels with the 3. So my final answer now is 6x over 9x squared plus 4 to the 2/3. Okay, number 20 we did in class together on the day that this homework was due, so I'm not going to waste your time by doing it again. Go see the write-up from class if you want to see my work for how to do number 20. Number 13, let's go. This is 1 over t minus 3 squared. Well, if you didn't know the chain rule and you you could do the quotient rule, I guess, here, but that's kind of like not the good way to do it. The good way to do it is to realize that this function is really just t minus 3 to the negative 2, because it's just 1 over t minus 3 squared. So we really need to be just very, very good at exponent rules. Well, okay, I'm very good. So here we go. How do I differentiate something to the negative 2? It's negative 2 something to the negative 3 back inside for the derivative of t minus 3. But the derivative of t minus 3 is just 1. And so I just end up with negative 2 over t minus 3 cubed. All right. How about 25? This is almost the exact same problem. Here, 1 over the square root of x plus 2 can best be written as x plus 2 to the negative 1/2, because that makes it more obvious that I need to use the power rule. So what's the derivative? Well, the derivative of something to the negative 1/2 is negative 1/2 something to the negative 3/2 back inside for the derivative of x plus 2. But again, that's 1. So maybe this is a bad practice or something for the chain rule, because if you just forgot to do the chain rule entirely, you'd still get this problem right. Okay, 29 was another problem that we did in class together, so I won't redo it. 49, okay, I have a lot to say about this problem, but I kind of said it already live in class just yesterday. In the book, they give you a big picture of the curve y equals e to the 3x, and they ask you for the derivative at 0. So okay, let's do it. The chain rule says that the derivative of e to the something is just e to the something back inside for the derivative of the something, and the derivative of 3x is 3. Therefore, dy dx at x equals 0, that's the notation for that, is, well, you just plug in 0 here, e to the 0 is 1, and so the answer is just 3. That's kind of all there is to do if all you want to do is do the problem. But the pretty picture they provided is supposed to sort of make you feel that if you compare e to the x and e to the 3x, that for the e to the 3x function there's been some kind of compression. And the factor by which we compress is different everywhere, but the factor by which we compress at 0 is 3. That's because this inner function, 3x, is increasing 3 times as fast as normal, where normal is just x. So, okay, good. That's one way of understanding the chain rule, but we sort of did that already, so I won't dwell on it. Number 60, this is a hard problem. Not conceptually hard, but in practice it's just hard to do, because this is a triple. In other words, this is a composite function inside another composite function. And here our book has a kind of unfortunate notation. They actually just leave off the parentheses entirely. So you have to kind of squint to realize that what they mean is 5 cosine cubed of pi t. And this kind of special exponent notation that we have for trig functions is useful until it's like not useful, like now, because it obscures the fact, possibly, that what's really happening here is we're taking cosine of pi t, multiplying that by 5, or sorry, we're taking cosine of pi t and cubing that whole thing and then multiplying by 5. So taking the step, as I always do, to rewrite it like that makes it more clear what's going on, and the answer is now, when it comes to differentiate this, that it's going to be 5 times whatever the derivative of this big thing cubed is. Okay, well, taking it one step at a time and applying the chain rule recursively, we see that the derivative of something cubed is 3 something squared back inside for the derivative of the something. So now I need to differentiate cosine pi t. What is the derivative of cosine pi t? Answer, it's a composite function, so I have to use the chain rule. The derivative of cosine of something is negative sine something, but then back inside for the derivative of the something. So everything is fine as long as you sort of enforce a little kind of discipline on what it is that you're doing. So I think it's pretty, well, I guess it's pretty clear that the derivative of something cubed is 3 something squared back inside for the derivative of that something. And then you just have to say, okay, now I need to sort of differentiate cosine pi t. How do I differentiate cosine pi t? Oh, that is also going to require the chain rule. Then you just do the chain rule there. Okay, so my final answer to this problem is like negative 15 pi cosine squared pi t sine pi t. It's possible that I did do this problem. I don't know. Maybe I did do this problem live in class. Can't remember. Negative 15 pi cosine squared pi t sine pi t. I think it's exactly like a problem that we did in class on the day that we learned the chain rule. Okay, let's do this one. 67. This is just kind of like a can you keep it all straight, man? What are we differentiating? We're differentiating sine of the cube root of x, and this is plus the cube root of sine x. So in other words, we're sort of differentiating a function and its the composite of two functions, sort of like in both ways. Okay, so this is just you just got to do this problem now. What is this derivative? Well, the derivative of sine of something is cosine something back inside for the derivative of that something. So the derivative of x to the 1/3 is 1/3 x to the negative 2/3 plus, I see I'm not really going to have space for this, plus, now I'm going to differentiate sine to the 1/3. Well, that's going to be 1/3 sine to the negative 2/3 back inside for the derivative of sine, which is cosine. So my answer to this number 64 is something like cosine of cube root x, this would be the normal way to write it, over 3x to the 2/3, and then plus cosine x over 3 sine x to the 2/3. This is the way of writing it with no negative exponents. Okay, and I forgot to mention that 57, 58, 59 we did in class. So I just did 60 and 64. So I guess I'm just going to make some quick space for the last two problems. 67 and 103. So that should be enough space. So let's go. What is 67? E to the root x. Y equals e to the root x. So this is e to the x to the 1/2. And so this is, once again, a chain rule situation. The outer function is the e to the function. The inner function is the x to the 1/2 function. So the derivative is, well, the derivative of e to the something is e to the something back inside for the derivative of the something. What's the derivative of x to the 1/2? 1/2 x to the negative 1/2. Okay, so final answer, this is e to the root x over 2 root x. Good. Last one. This homework is actually maybe not that hard. I don't know. 103 says find the second derivative of sine of x squared. So sine of x squared. Okay, so this is just a bit of a drag actually. So let's go. I take the derivative. What is the derivative of sine of x squared? Well, chain rule says the derivative of sine of something is cosine something back inside for the derivative of the something, which is just 2x. Alright, that part was easy, but now if I want to take the second derivative, well, now I have to differentiate this function, which just is going to require the product rule, but chain rule inside of product rule. So let's kind of be careful about it, or something. So, yeah, derivative of the first. What is the derivative of cosine of x squared? Well, the derivative of cosine of something is negative sine something back inside for the derivative of the something, which is 2x. So everything I just did is like the derivative of cosine of x squared. Yep, the derivative of negative sine of something back inside, yep, times, so the derivative of the first times the second plus the first cosine of x squared times the derivative of the second, which is just 2. So what do I end up with here? Something like negative 4x squared sine of x squared plus 2 cosine of x squared. Okay, not too bad. I'll post this in a minute. Bye.